All right. All right. Number 4. What z-score is in the 74th percentile? He's asking for the z-score, guys. That means you have to use the inverse norm. Let me sketch this for you. Watch. '74th percentile means 74%. I want to shade 74% from here. 74%. If I say my score in the 74th percentile, it means I did better than 74% of the students. So that means 74% of the students did lower, just than me. Lower means to the left. So to shade 74%, you shade it like this. It's about 50%. This is 50% right here, guys. So this is 74%. And if you change it to a decimal, guys, it will be 0.74. So to find z, it's inverse norm. It's going to be positive. And if you ask me why positive, because that's more than 50%. Any area that is more than 50% will lead to a positive z-score. You put 0.74 here, and you put 0, and you put 1. Let's do it together. So I'm going to go second, distribute, inverse norm, 0.74, comma, 0, comma, 1. 0.64, 0.64. We need 2 decimal places. Okay. Number 5, it was a probability questions. It's a probability, guys. You can see here. So we did normal CDF. Okay. 6. On a standardized test, scores are normally distributed with a mean of 400 and a standard deviation of 80. Now, he gives you the mean and he gives you the standard deviation. What score must one have to be in the 80th percentile? So 80th percentile means you did better than 80% of the students. Well, 80%, guys, it has to extend above the middle, so it will be somewhere here. And we need to find the score of students who scored in the 80th percentile, means they did better than 80% of the students. So what would be the X value? Can you guys help me input here the values? It's an inverse norm. What would be the first number that I put there?
0.80.
0.80. And now what's next? Now it's X, it's not Z. He doesn't want Z. He wants the X value, the raw value. He gave me the mean and the standard deviation.
Want to be 80 or 400.
400 and then what? 80. All right. I mean, if you put 0, 1, you're going to get the Z-score, but he doesn't want the Z-score. So he wants the X value. Then that will give you the X value. And definitely the answer, guys, is going to be more than 400 because 400 is sitting right here. That's the mean, the average. It's in the middle. So definitely the answer will be 400, more than 400. Let's check. Second, distribute. These are the formulas, guys, the 2 formulas that you will be using in the entire chapter. What was the standard deviation? 80. Let me double check. Yeah. Look, inverse norm, 0.80, 400, comma, 80, and close. And here you go. 467.33. Now, if you're doing this exercise online, you might be asked to round to the nearest whole number. So that will be 467. All right. Next exercise. That was wrong here. Number 8. Find the 25th percentile of the normal distribution of X. In other words, find the value of X. And he gave me a mean. Let me see, where is the mean in the standard deviation? Okay. Find the 25th percentile. That means, guys, he's giving you the area, which is 25%, and he wants the X value. Actually, this is not an 8. This is a continuation of 7. So I need the mean and the standard deviation from 7. And suppose that the diameter of a certain car component follow a normal distribution with the mean of 10. So that's the mean. And a standard deviation of 3. So how do you find the 25th percentile? Let me show you a sketch, guys. 25th percentile. You agree with me, if I shade 25% of this curve, starting from the left, it's not gonna cover up to 50. It's gonna be somewhere here. This is 25%, guys. And he wants this X value. So can you guys help me find this X value? It has to be less than the mean. The mean is 10 here, guys. Anything less than 50% will be less than the mean. Anything over 50% will be above the mean. So it will be inverse norm. And can a student tell me what the 3 arguments would be here? Yes? So we have what, 25%?
25%, 10, and 3.
10 and 3. That's it. Let's do it. Okay, so let's do 0.25, comma, 10, comma, 3. It's 7. As I told you, it's less than 10 because it's below 50. So it's 7.98. There you go. Okay, we started with this exercise last time. This is actually, guys, your assignment, your chapter 5 assignment. I gave you very much the same exercise, but different numbers. I asked you about the probability of X greater than, a probability of X less than, probability of X in between. Find the 80th percentile. The 80th percentile means what's the X value for which 80% of the values are below that one. I sketched it right here. You see this is 80% and we did an inverse norm, 0.8, that's the area. The mean is 8 from the beginning of the exercise. The standard deviation 1.5 and you get 9.26, which is bigger than the mean. Anything over 50%, guys, is gonna lead values that are bigger than the mean. E and F, we cannot do them yet until I explain section 5.4, but I'm gonna do part G now before I take you now. So that will be a segue to section 5.4 from here. What would be the minimum weight of an orange that places it in the top 10% of weights? So top 10%. You draw the normal curve, you draw the mean, which is what, 8 ounces. And then the standard deviation, 3 standard deviation from this side and 3 standard deviation from that side. Here's my question to you guys. Where would a top 10% of weight be? To the right of the mean or to the left of the mean?
To the right.
To the right. That's a top 10%. So you shade an area which is 10% here. Look what you do. Mark it. And change it to a decimal. We're going to need it as a decimal. He wants the X value here. What would be the minimum weight? He's not asking for a probability. He gave you the probability. He said it's 10%. Any percent, guys, is a probability. So he wants the X value. Okay. In order to find the X value, we have the inverse norm. But I'd like to bring to your attention something here. Unless if you have the newest calculator, you don't have to worry about it. But with most calculators, you need the area to the left here of the target. Target value. you need the mean, and you need the standard deviation. Watch here, guys. Please pay attention to this exercise. He gave me the area, and it turned out to be a right tail area, 10% to the right. But the formula requires the area to the left. So if 10% is the area to the right of X, what would be the area to the left of X?
90.
90%. Now, if you have a calculator, guys, that says left, right, middle, you can put right and keep it at 10%. Then the calculator understands that the 10% is an area to the right. But if you don't, the other program that's built on the calculator requires the area to the left. So I'm going to put 0.9. And then I'm going to put the mean, which is 8. And I'm going to put the standard deviation, which is 1.5, and find the answer for you. Second, distribute 0.9, comma 8, comma 1.5. Watch. I got 9.92 ounces. Now, let's say, guys, you made a mistake and you put 10% here. I'm going to show you how to use common sense to know that your answer is wrong. Let's do the 10%. So put 0.10, comma 8, comma 1.5. Okay, 6.07 ounces, 0.8 ounces. Where, guys, the common sense tells me that this is wrong? Can someone tell me? I should know from the answer itself that this is a wrong answer. How? Any feedback? Any comments, guys? Why, if a top 10% weight can't be 6 ounces? That doesn't make sense. Why is that? How could you be a top 10% and your value is below the mean? The mean is 8, guys, and 6.07 is below the mean. You cannot be like a top 10% student. Can a student be in the top 10% and his or her score be below the mean, the average? That can't be. That's not possible. So it has to be above the average. And look at the value here, 6.07, guys, is below the mean. That can't happen and be in the top. Yeah, you can be at the bottom 10%. Actually, this is the bottom 10%. So if this question was about the bottom 10%, you will shade your 10% right here. And then that will be a correct answer. But top 10%, guys, it has to be more than the mean. I hope that makes sense to you. All right. Number 10. We can do that without section 5.4. A firm's marketing manager believes that the total sales for next year will follow the normal distribution with the mean of 2.5 million and a standard deviation of 300,000. First of all, guys, let's learn how to write the 2.5 million. So it's 2,500,000. So it's going to be written like this. 2,500,000. What's the probability that the firm's sales will fall within $150,000 of the mean? Do you guys know what that means? Does anyone know what that means? I put in between, as you can see, for the answer. What does it mean for the sales to fall within $150,000 of the mean? No feedback. It will be either 150,000 below the mean or 150,000 above the mean. So you need to do 2,500,000 minus 150,000, and you need to do 2,500,000 plus 150,000. So that will be, guys, 2,350,000 and 2,500,000, and add another 150,000, 2,650,000. And that will be normal CDF in between, it's very straightforward. 2,350,000, the lower bound. 2,650,000, the upper bound. The mean is 2,500,000. Just be careful with the zeros, and the standard deviation is 300,000. Okay, can we all try to do this? I'm gonna pause for a second just to make sure that students know how to do this. So the answer is 0.3829. B, determine the sales. So he wants the X value now that has only 9% chance of being exceeded. Watch, guys. This is the 9% right here. Only 9% of sales can exceed this, so it has to be on the right. So X is not, we need this X value. That's the area, 9%. Or write it 0.09. So X will be, guys, inverse norm. And we'll write it right down here. Okay. The formula requires, again, the area to the left, guys. He gave you a top 9% here. We need the area to the left, which is 0.91. You subtract it from 100%. And then you put the mean, which is 2,500,000. Then you put the standard deviation, which is 300,000. And let's do this and see what the amount of sales is. Second, distribute. I cannot emphasize enough, guys, how important those two formulas. They're gonna take care of every single problem in the homework by using those two formulas. Normal CDF, inverse norm, those two formulas. Inverse norm is used to find the X value, and normal CDF is used to find the probability. So that would be 0.91, comma, 2,500,000. Enter it properly, guys. And then 300,000. Okay, so it's 2,902,227 if I went around to the nearest dollar sign. I'll write it down. That's the answer. All right. Let me see next. Okay, this is all probably section 5.4. So now, guys, we're gonna go and show you this applet. So I'll just want you to relax and make some observations with me as we watch this applet before we go back and do the remaining problems that involve section 5.4. So I'm gonna stop sharing here. Okay. What we have here, guys, we have a bell-shaped distribution with the mean and the standard deviation. I chose the mean to be 100. And you notice in a bell-shaped distribution, mean and median are the same. So the mean is 100. And I selected the standard deviation to be 12. And look, it looks nice bell-shaped curve. You have to remember, guys, when we work with a population, we cannot survey the entire population. We cannot work with the entire population. So we have to select samples from the population. And based on the results from the sample, we can make conclusions about the population itself. What we have been doing so far, guys, up until section 5.3 and including section 5.3, we pick one individual and we find it's a probability. Now, what we're gonna do differently in section 5.4, we're gonna select a sample and we're gonna find the average of those samples. So I'd like you to watch what's happening, you know, just as I start this applet and give me some observations. If you watch the video that I sent you, you already know what I'm talking about, but if you didn't, please pay very good attention to what I'm gonna do. Okay, I'm gonna select samples of size 9, guys. So This is a population. I can select as many samples as I want. This population has millions and millions and millions of observations and values. So we're gonna select samples of size 9. And then we're gonna ask this applet to find the mean of the sample. So what the applet does, guys, it will pick 9 members from this, and then it will add up the 9 values and divide by 9 and give me the sample mean, and it's gonna graph it below here. You will see. Okay, so watch, I'm gonna do it one time. You see, it's picking 9 values, watch. Then it's gonna find the average. See, it did find the average. It's very close to 100, as you can see the average right here. Okay, let's pick another one. This is the second average. They're not the same. Different samples lead to different sample means. It will find a different average. Let's do one more time just to have you see the visual now. See, next to it, it turns out to. Now I wanna pick, instead of picking one sample at a time, I'm gonna pick 1,000 samples of size 9. What the applet is gonna do, guys, and it's a blink of an eye, it's gonna calculate the mean, the sample mean of each of those samples and plot them, you know, down there. So it's gonna do it 1,000 times, guys, in less than 1 second. Watch. There you go. So what you see here, guys, is a distribution of all those sample means that the applet did. It's about 1,003. Why 1,003? Because I did 3 individually, and this is 1,000, guys. I'm gonna do another 1,000 times, guys. Here. One more. There you go. We did 9,000 samples, guys, of size 9. What the applet did, it graphed, you know, all the means. So it did it 9,000 times and plotted all those sample means in here. And this is the graph of the sample means. This is the actual population, and these are the samples right here, guys. And this is what I'd like you to notice here, guys. Do you notice that the mean of those 9,000 means it's 100, and the original mean was 100 as well? Look, this is the mean right here, and look at the mean, it's right in the middle right here, 100. So both the original population and the new population of the sample means have the same mean, which is 100. Now you might tell me it's 100.0007, but eventually, guys, it's gonna flatten out and balance to 100, so it's 100. Now, do you guys agree with me that the green curve has a smaller standard deviation than the black curve? And the answer is yes, you should agree. Why? Because look at the data, it's more widely spread in the original population than the green one. The green one is narrower. It's always better, guys, to work with a population that has a smaller standard deviation because we have more consistency this way. Now, what is the standard deviation of the original population? It's 12. What is the standard deviation of the sample means? It's about, if you round this one, guys, to the nearest whole number is 4. I'd like you to do something for me. I'd like you to take the square root of 9. The square root of 9 is what, guys? 3. Take 12 and divide it by 3. What do you get? If you take 12 and divide it by 3, there you go. You will get 4. So actually, guys, you don't need to watch the applet to know what the standard deviation of the sample means is going to be. We know it is going to be the standard deviation of the original population divided by the square root of the sample size. Well, square root of 9 is 3. Divide 12 by 9, guys, you get this number, which is 3.9936, but it's 4. It's very much a 4. What I'm going to do now, guys, I'm going to change this one to 16. And I'm gonna pick samples of size 16, and I like it to observe. Watch. I'm gonna pick 1,000 times. Another 1,000. This is all happening in real time, guys. This is how fast the applet is. I want to pick 15,000 samples. There you go. Okay. The population has a mean of 100 and a standard deviation of 12. Look at the population of the sample mean, guys. It has a mean of 100 as well. This is 99.966, but eventually it will balance out, you know, to 100. So it's 100, very close to 100, 100, 100. Now watch the standard deviation, guys. Without even looking at the 3 right here. I like you to do this for me. Take the square root of 16. Square root of 16, guys, is 4. Divide 12 by 4. What do you get? 3. There you go. This is the standard deviation. And look at the population of the sample means. It's much narrower population. So it's better to work with the sample means rather than working, you know, with the original population because it has a smaller standard deviation. Now, guys, I'm going to change the sample size to 36. And I'm going to change this population, not to a normal population, any population. So I'm going to make it skewed to the right. Watch. There you go. So the mean, well, look at the mean. The new mean is 91.0358, and the standard deviation is 19.0796. I'm going to draw samples of size. So remember, the original population is not bell-shaped, guys. That requirement is not met. Let's see what's going to happen when we draw samples of size 36. Watch. I'm going to do 10,000 samples. There you go. Okay, what do you notice here? The shape of the sample means is bell-shaped, whereas the original population is not bell-shaped. And remember, guys, all the work that we've been doing in chapter 5 based on the fact that we have a bell-shaped distribution. So the sample means are bell-shaped. Watch. Oh, they have the same mean. Look at the mean here, 91.06, and look at the mean right there, 91.03, which is very much the same. If I do more samples, we will come very close to 91.06. But I like to watch the standard deviation, guys. If you have your calculator handy, I would like you to take 19.0796 and divide it by square root of 36. Square root of 36, guys, is 6. So let's see, what's 19.0796 divided by 6? If you can do the math with me, I appreciate that. I got, guys, 3.18. And look here, it is 3.18. So even if the population originally is not bell-shaped, and we draw samples of size 36 here, it turns out that the new population of sample means is bell-shaped with the same mean and a smaller standard deviation. And then we know how to find the standard deviation. We just take the original standard deviation and divide it by the square root of 36. Let's try another one, guys, here. I'm gonna make it 100. So the sample size 100. I'm gonna change this population, make it skewed left. Watch. There you go. So I got a mean of 107 and a standard deviation of 19, and let's do 1,000 times. One more. Let's do 10,000. There you go. Okay, watch, guys. The original mean is 107.9557. Look at the mean here, same thing. 107.9364, very close, so almost the same mean. Now look at the standard deviation, guys. The reason I chose 100 because it's easy to find the square root of 100, it's 10. If you divide, guys, 19.5326 divided by square root of 100 by 10, what do you get? You get 1.95326. Watch. It's almost the same. If you round them, you will get pretty much the same answer. So this is the standard deviation. And look at the population itself here. It looks like it's bell-shaped with a much smaller standard deviation. Look how wide the curve here, guys, is, and look how wide it is there. What I'm gonna do after this, guys, I'm gonna take you back to the chapter 5 guided notebook and show you how to work with this section. You're not gonna see a big difference. It's just a small change, and then that should be it for this chapter. So I will stop this applet and go back to the guided notebook for this. So we've done the simulation. All right, the central limit theorem. Use mu for original population and mu of x bars for the mean of the sample means. Okay, let's go to the next page. There you go, guys. Use sigma for original population and sigma of x bars for mean of sample means. So this is what we observed, guys. That was the original population. Watch. It has a mean mu and a standard deviation sigma, and that's the curve of the sample means. You notice it was a little bit narrower curve with the same mean but a different standard deviation. So what is the conclusion that we can make here? The mean of the sample means, which we call it mean of x bar stands for sample means, is equal to the original mean. You observe that the means were the same. The standard deviation, which is here, right here for x bar. So this is the original population x, guys, and this is x bar, mu of x bar. The standard deviation of the sample means is equal to the population standard deviation divided by square root of sample size, which is sigma of x bar, guys, equals sigma divided by square root of n. You will see how we're gonna apply this in a second. When the original population is bell-shaped, normally distributed, then the distribution of the sample means is also bell-shaped. Regardless of the sample size n. When the original population, guys, is not normally distributed, I showed you like a distribution that is skewed to the right, then the distribution of the sample means is also bell-shaped. But I use the sample size, which is a bit large. I use 36 and 100. If the sample size is more than 30, a large sample size, guys, means 30 or more. I use 36, I used 100, but the cutoff number is 30. When he says use a large sample size, he's referring to 30 or more. So 30 is the cutoff number. So look, guys, this population is not normal, the original population, but if you do the sample means, you will get a normal population. Sample size is more than 30. This population is normal. If you do sample means, you're gonna get also a normal population regardless of the sample size. So if your original population is bell-shaped, it doesn't matter what the sample size is, you're gonna get always a bell-shaped curve when you do the sample means. But if your original population is not bell-shaped, you need to choose samples of size 30 in order to guarantee that the sample means will be bell-shaped as well. This is the central limit theorem, and I'm going to show you how to apply this, guys. I think probably this is one of the most important topics in this book because everything else from now on is based on the central limit theorem. And let's do those two applications of it, and then we'll do some more exercises to apply the theorem. Okay. Exercise 11. Cellular phone bills for residents of a city have a mean of 63 and a standard deviation of 11. Random samples of 100 cellular phones bills are drawn from this population. So the size of the sample, guys, is 100 here. That's n. And the mean of each sample is determined. Find the mean and the standard error of the mean of the sampling distribution. Okay, let me tell you what the standard error means here. It means the standard deviation of the sample means. So he wants the mean of X bar and the sigma of X bar. Well, I already stated that for you guys. The mean of X bar is the original mean, and the sigma of X bar is sigma over square root of n. So to answer this question, guys, it's very straightforward. You just put the mean of X bar equals what? $63. And the sigma of X bar, they call it standard error of the mean. So when you do your homework, guys, online, and it says find the standard error of the mean, he wants the standard deviation of X bar, which is sigma over square root of n. So that will be what? 11. What's the standard deviation? 11 divided by square root of 100. 11 over 10, which is 1.1. You see how small the standard deviation is? It's 1.1, but the original standard deviation of the population is 11. So that's why it's better to work with distribution that have a smaller standard deviation, which is X bar. Okay, let's do number 12. It's the same thing. The training heart rates for all 20-year-old athletes are normally distributed with the mean of 135 beats. So the mean is 135, guys, and standard deviation is 18. Random samples of size 4, so n is 4 now, are drawn from this population, and the mean of each sample is determined. What's the mean and the standard error of the mean of the sampling distribution? So he wants mean of X bar and sigma of X bar. Well, guys, just like we did before, mean of X bar is the same as the original mean, which is what, 135. Standard deviation will be sigma over square root of n, which is 18 divided by square root of 4. And actually, guys, if you remember last week, I did do some practice with algebra with you and how to do something over a square root of a number. That's why we're doing it, because of this. So you should know how to do that. So if you are using your calculator for something like that, this is how I would do it. I'll put 18 and and then divide, and then go to square root. So second and x squared, and then put 4. Well, we know what the square root of 4 here. That's going to be 9. All right. So now 13, and now the real application of this theorem. Furnace repair bills are normally distributed with a mean of $266 and standard deviation of 15. So mean, guys, is 266 and standard deviation of 15. If 36 of these repair bills are randomly selected, so n is 36, guys. Please pay attention to this question. This is the application of section 5.4. What's the probability that they have a mean cost between $266 and $268? All right. He says, what's the probability that they have a mean cost? So the sample mean, what is, guys, what is the sample that we use for the mean? We don't use X. What do you use, just to denote the mean, the sample mean?
Mu with
No, mu is for population mean.
X
We-
bar.
X bar, exactly. So guys, the big difference, the only difference between the previous section, section 5.4, he will be asking you about the probability of the sample mean, a probability of X bar. See, and how can you tell? Look, this is the word, guys. They have a mean cost, so the X bar, between 266 and 268. Okay. It's normal CDF. It's a probability. I told you, and I'll stick to my word, there will be only 2 functions in this chapter. Normal CDF and inverse norm. Okay, we need the lower bound. 266. The upper bound, 268. The mean, which is what? 266. And now we're gonna pause here, guys. The only difference that changes from the previous sections to this section is when you are finding the probability of the sample mean for X bar, your standard deviation is not the original standard deviation. So can you guys tell me what is it that I'm gonna put right here? Anyone? What does the theorem say? The theorem says it's gonna be 15. And then what?
Over 266.
Not divided by 260, divided by square root of n. What's n here?
36.
36. If you guys put 15 and don't make any changes, don't divide by square, you're gonna get the wrong answer. So every time you work with X bar, guys, you do the same work that you learned in previous chapters. The only thing that you have to change here. So you have to make this sigma over square root of n. If you don't make any change, guys, and you just make it as 15, that means you didn't use the 36. I won't give you anything in mathematics that you don't use in a problem. We don't. If we give you guys some numbers in a problem, you must use all of them. So if you end up not using the 36, something went wrong. And the 36 can be used right here.
Is it always going to be over the mean?
Not over the mean, over the square root of sample size. Yes. Anytime the question is about the mean, you do this. And we're going to demonstrate 3 or 4 examples, guys, so you will see it more clearly in a second. So let's do this. Normal CDF, 266, comma, 268, comma, 266, comma, and look, 15. And let's say we don't know what square root of 36 is. Not a big deal, guys. Just put 15 over and put square root of 36. And then close. Watch. Ready? Here you go. A common mistake that students make, and they tell me, Mr. Bazzi, I used the right formula, but I just got the wrong answer. They forgot to put the division sign here, so make sure to put division. It's 15 divided by square root of n. So 0.2881.
Can you do this with the other calculator?
Yeah. Let's do this with the other calculator. So go second and distribute, normal CDF. Lower is 266, upper is 268, mean is 266, and standard deviation, 15 divided by square root of 36. There you go. And then when you paste, you're gonna get back to the previous calculator, same formula. And you should get the same answer. Okay. Next, let's do exercise 14. And then I'll go back to the question which is similar to your assignment and finish the last 2 parts of it as well. And then we'll go and visit the assignment. A farmer was interested in determining how many grasshoppers were in the field. He knows that the distribution of grasshoppers may not be normally distributed. If his original population is not normally distributed, if he picks a sample size, he has to pick a sample size of more than 30, guys. So let's see if he did that. In the field due to growing conditions. As he drives his tractor down each row, he counts how many grasshoppers he sees flying. After several rows, he figures that the mean number of flights to be 57 with a standard deviation of 12. What is the probability that the farmer will count 60 or more flights on average? When he says on average, he's talking about the mean, guys. So what's the probability that the sample mean is 60 or more? So he wants the probability of X bar more than 60. In the next 40 rows, can you guys tell me what the number 40 represents? What's simple? What would that be? So we want to find the probability on average that he'll have a 60 grasshoppers or more in the next 40 rows. He was counting how many in each row, how many grasshoppers in each row. So that would be what the sample size, guys, which is n equals 40. So can you guys help me? What would be the lower bound here?
60.
Yeah. What's the upper bound? This is greater than million. Mean is 57. And look at the standard deviation, guys. It's not 12. It's 12 divided by square root of 40. That's a big difference between this and the previous section. So let's do this. Second and distribute. Normal. We don't use normal PDF, guys, in this chapter. Only normal CDF. So we get 60 to begin with. Million. 57. And then 12 divided by, watch, square root of 40. And you get 0.0569. Now, if you were doing this and you were asked to change it to a percent, guys, just multiply by 100%. And if you multiply by 100%, it will be 5.69%. Just move the decimal point 2 digits to the right.
We have to multiply by 100?
Yeah, just multiply by 100% and then just move the decimal point 2 digits to the right. That would be 5.69%. Because sometimes he will ask you a question, instead of saying probability, he says what percent. If he says what percent, he wants the probability, but he wants you to change your answer to a percent.
Oh, okay.
Okay, let's. So back to question 9, doing the remaining parts that have to do with section 5.4. That's section 5.3. To make it easy for you to review, guys, when you review those sections. Okay, watch. If 9 oranges were randomly selected, so n is 9, what is the probability that their mean weight is less than 11.2 ounces? Guys, please remember that. Take a note of it. If I say the mean weight, I mean I'm talking about X bar, not X anymore. So you need to put X bar here. Less than 11.2 ounces. Okay, who would like to volunteer and tell us what the 4 arguments are? What's the lower bound?
-1,000,000.
All right. What's the upper bound?
11.2.
What's the mean?
Mean is 8.
8. And what's the standard deviation?
It is 1.5 over the square root of 9.
Excellent. This is all, guys. This is all. If you have a sample size, use it in the problem. Divide by the square root of the sample size. That's it. So let's do it. So we go second and distribute. Normal CDF. I got -1,000,000. And again, guys, when you use -1,000,000, this is the sign for negative right here. Then 11.2. Then 8. Then 1.5 divided by square root of 9, which is, oh, sorry, 3. I'm just going to put 3 here. Okay, 0 point. It's almost 1. If you round it, it's going to be 100%. So that means all the oranges are going to be, they have weight less, on average, weight less than 11.2 ounces. Okay, next part, F. Watch, guys. If 17 oranges are randomly selected, so N is 17 now. What's the probability that their mean weight is more than 12 ounces? Okay, I'm going to change it, just make it 11 ounces. Okay, who would like to help us answer this question? What do I put here on the left? He says, what's the probability that their mean weight? You see the word mean, guys? Mean weight, sample mean. So not X we use X bar. More than 11. Okay. Normal CDF. Okay, guys, what goes in here? I'm ready.
11
11. Then what?
million.
Then the mean, which is what? Same.
8,
Then the standard deviation.
1.5 over square root of 17.
Exactly. Not square root of 9, guys. We're done with 9. We answered that in part E. Square root of 17. And watch, guys. Cannot make it any simpler than this, guys. So you need, if it's making sense to you now, great. If it's not, I would like you to go back and review everything that I provided in this chapter. Actually, in addition to this, if you flip the pages, you're gonna see that calculator shortcuts and how to use the normal CDF and the inverse norm later in this handout. So we're gonna go second distribute, normal CDF, 11, mean is 8. Don't forget to change this, divided by square root of 17. Don't worry what square root of 17 is. Let the calculator handle that. So divided by square root of 17. There you go. All right, I got 8.267 E minus 17. Do you guys still remember what's the interpretation of E minus 17 is? Can someone tell me?
The decimal moves 17 times to the left.
Yeah, that means it's 0. So it's almost 0. Once you see an E minus, guys, your answer is almost 0. So I'll just put 0. So the chance, guys, that you pick a 17 oranges and figure out their average weight, and to be able to get an average weight of those 17 oranges more than 11 ounces is 0. It's not going to happen. It's almost 0. That is what it means. Okay. Now I'm going to take you back to your assignment. And if you like to take notes while going over this, feel free to do so. So just 1 second. So for example, guys, this, for the first one, what's the probability of the one randomly selected? It's 1, we're not doing samples, guys. Will weight less than 185 pounds. So you have to start. Oh, it's not allowing me to. Annotate here. Do you guys, can you guys see the screen?
Yes.
Yeah, just it froze on my side. I might have to stop this, guys, and then try again. My mouse just got frozen and the entire screen is frozen. Don't go away. Yeah, I cannot move anything on the screen. So guys, if anything happens, don't go away. I'll be right back. I need to reset this. So we might have to do 2 recording. I'll continue the recording from this part right here. Yeah, I can't even stop any. Okay, I'll be right back, guys. Give me 1 minute. Don't go.